Hi, my name is Adam Fitzpatrick. I'm speaking to you today on behalf of Group 2, consisting of myself, Brian, Gordon, and Anwar. Today I'm speaking about the Archimedes principle, one of the most basic yet most vital principles of fluid mechanics. Archimedes' principle states that the buoyant force is equal to the weight of the fluid displaced. So what that means in mathematical terms, I have it here, is the buoyant force is equal to the volume of the object times the density of the water, and then times gravitational acceleration. Another interesting thing that you can derive from Archimedes' principle is specific gravity. Specific gravity of an object is the density of the object over the density of water. If your specific gravity is over 1, the object will sink. If it is less than 1, the object will float. Objects where the specific gravity is very low has a greater tendency to float than objects whose specific gravity is less than 1 but near 1. So basically what I'm going to show you is a quick example that I've prepared. I have an 8-pound bowling ball and a 16-pound bowling ball. And I believe Archimedes' principle, just as with any engineering principle, is best explained by a free body diagram. So I'm going to go ahead and get started doing that. So you have your 8-pound bowling ball right here. Your buoyant force acting upward. Buoyant force is equal to the volume of the object times the density of the water times gravity. For the 8-pound bowling ball, that is equal to 54 newtons. Here I have the properties of our test subject. It has a mass of 3.363 kilograms and a volume of 0.0055 meters cubed. Over here, I'm actually not going to finish that free body diagram yet because I want to prove a point. We have a 16-pound bowling ball right here, and even though it is heavier, it's a larger mass, it's a greater weight of force acting downward, you'll see that the buoyant force acting upward is actually the same. That is because the volume is the same. So once again, buoyant force is equal to the volume of the object times the density of water times gravitational acceleration. So once again, that is equal to 54 newtons. Now, it's the force acting downward due to the weight of the bowling ball that varies. Actually, for the 8-pound bowling ball, it's obviously going to be half of what it is for the 16-pound. So I've prepared that, and that is equal to the mass of the object times gravitational acceleration, and that is equal to 71.22 newtons for the 16-pound bowling ball and 35.61 newtons for the 8-pound bowling ball. Now you'll see for the 8-pound bowling ball, the buoyant force acting upward is greater than the force due to weight of the bowling ball. What that tells us is that the object's going to float. The weight of the water overcomes the weight of the ball, and the ball floats. However, for the 16-pound bowling ball, the force acting downward due to the weight of the ball exceeds that of the buoyant force acting upward of the ball, and the ball is going to sink.
We measured a standardized weight, which came out to 200 grams. It was measured on a scale which measures weight as against the acceleration of Earth's gravity. But when we submerged it, it weighed 175.5, which is less.
In this video, we're gonna take this orange and put it in this bowl full of water and see what happens. As you can see, the orange floats. Now let's remove the rind. Put the orange back in the water and see what happens. The orange sinks. And that is nature's way of showing that life jackets can save your life.